Okay, so we're going to go over kind of like some guiding principles to help you draw these bond line structures appropriately. And then we're going to get some practice at actually drawing them from kind of complex Lewis structures. Okay, so first thing to note, again, as I've already mentioned, is that in these bond line structures, all the carbons are essentially the points and vertices of these little zigzag lines. Okay, so in one of the first taking a Lewis structure and drawing a bond line structure from it, what we're going to do is we're going to put all the carbons in essentially a zigzag. Okay, so for example, let's say that we have this Lewis structure over here on the left. For me, a lot of times I like to go ahead and count carbons so that I keep track of how many I have and how many I'm going to need in my bond line structure. So let's say we'll call this guy carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. Now, the first thing we're going to do in taking this Lewis structure and drawing the appropriate bond line structure is we're going to remove all the hydrogens. So remove all hydrogens, and we're just going to go ahead and keep that carbon chain backbone, right? So let's say we have carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, okay? Now, the next thing we're going to do is we're going to go ahead and put those carbons as is in a zigzag, right? So our next step here is taking these guys and zigzagging them, right? So we can start, let's say, with carbon 1 down below. It's going to zig or zag, whichever one, up to carbon 2, to carbon 3, to carbon 4, to carbon 5. Or if you wanted to do alternately, you could have carbon 1 up here. It could go down to carbon 2, to carbon 3, to carbon 4, to carbon 5. Both of these are essentially equivalent, right? And so both of them are acceptable. Okay, so then after we have zigzagged, what we're going to do is we're just going to remove the carbons, right? So remove the actual C's from what you've drawn, and you're ideally going to be left with a nice bond line structure, right? So essentially this guy goes 1, 2, 3, 4. So that's all we're going to do is go 1, 2, 3, 4, and that's our bond line structure, right? Again, all of these vertices and all of these endpoints are carbons. So we have 1, 2, 3, 4, 5. We don't draw any hydrogens, and that's the appropriate bond line structure. I could have done the same thing for this guy over here. He had gone 1, 2, 3, 4, and so I could also just be left with 1, 2, 3, 4. And again, what we're looking for here is 1, 2, 3, 4, 5 carbons. All of those little points are carbons. Okay, so that's kind of like just a brief run view of guiding principles of how to take a Lewis structure and turn it into a bond line structure. A couple other things to note. So first off, let's say that we have a double bond. When we draw those structures, we want to make sure to keep the bonds as far apart as possible. So for example, let's say we had a structure like this. We have carbon, carbon. We've got a double bond here to oxygen. And these guys are just CH3 groups, right? Let's say I wanted to take this and I wanted to turn this into the bond line structure. So again, I'm going to go ahead and count my carbons. We have 1, 2, 3. I'm going to remove all of the hydrogens, right? So that's just hydrogen. That's not other atoms, like what we call other heteroatoms, so anything besides carbon and hydrogen. So I'm only going to go through and remove these guys from my structure. So we're left with carbon 1, carbon 2, carbon 3, and again we still have this double bond to oxygen here. Now again I'm going to zigzag, right? So I'll go back to black here. I'll start with carbon 1 down, carbon 2, and carbon 3, and then I'm going to keep my double bond here. And this is kind of the point of this, where we want to make sure that we have all of these bonds as far apart as possible. This carbon that has the double bond to oxygen is sp2 hybridized, right? So if you remember from last chapter, sp2 hybrid orbitals is what this carbon is using. That tells us that it is trigonal planar. So trigonal planar, and these bond angles ideally are about 120 degrees, right? So we want to try to keep that geometry, which is kind of what we have right now, right? This does kind of look like a trigonal planar structure with the zigzag that we have created. What we would not want to do is, say, have our carbon 1, carbon 2, carbon 3, and then let's say put the double bond down here. This would be bad because again, these are really steep bond angles. This is a very large bond angle, so this is not what we want, okay? So make sure when we do have a double bond that we're trying to maintain that trigonal planar geometry. And so in doing so, we would come down here, taking this guy, turning it into the complete bond line structure. All we do here is take off the carbons. So we've got 1, 2, 1, 2, and then again, we're gonna go ahead and show that double bond up. So this would be the correct structure. You could also have gone carbon 1 down to carbon 2, up to carbon 3, and then the double bond would go down here. This guy would have turned into, so these guys are synonymous, but again, in the actual structure, we're trying to keep those bonds as far apart as possible. Okay, so a couple other little things to note. When we draw single bonds, the direction that we draw them in, and this is what I tried to illustrate in that first example, the direction that we draw them in is kind of irrelevant. So for example, let's say we had a structure that looked like this, right? So let's say I could draw that like that. I could also equivalently draw that like this. And a good way to kind of keep note of that is just to say, okay, I've got 1 carbon, 2 carbon, 3 carbon, 4 carbon, 5 carbon, and then I've got like a methyl or a CH3 group that bounces out from what we would call the carbon 3. Over here, I have the exact same thing. I've got 1, 2, 3, 4, 5, just like I did over here, and I've got this methyl group that bounces out from the carbon 3, okay? Another way that we could draw that is something like this, right? Because again, we're just keeping those zigzags. So if we're looking for just the longest like chain of carbons, we've got a carbon 1, 2, 3, 4, 5, which is the exact same that we had for these guys over here. And again, we have a methyl group that bounces out from the carbon 3. So methyl group, what I refer to that as a CH3 group, that's what this guy is on the end. Because if you drew in the hydrogens here, you'd see that there are 3 hydrogens surrounding it. So all of these structures are equivalent. They're the exact same. They are not constitutional isomers or anything like that. And then anytime we have heteroatoms that have hydrogen attached, we also have to draw the hydrogen, right? So we do ignore hydrogens that come off of carbon. So carbon-hydrogen bonds we will ignore in our bond line structures. But let's say that we had something, or let's start with the Lewis structure. So something like this, where we have, let's say an alcohol group. We don't know what alcohol groups are, but we'll go over that in a second. So here we have an oxygen, right? And that oxygen also has a hydrogen bound to it. So when we go through this first step of removing hydrogens, we're not going to remove this guy. This guy's going to stay, right? So it's only these guys that are going to come off. Anything that has, or any heteroatom, so anything other than carbon that has a hydrogen, we're going to keep on in the bond line structure. Okay, so again, if we went 1, 2, 3, 4, 5, oh, and we have a hydrogen here. Also, never draw carbons with more than 4 bonds, but always make sure they actually do have 4 bonds, as I made a mistake there. Okay, so we have C1 going up to C2, going down to C3, going up to C4, right? But we're going to go ahead and draw our oxygen here, and then it's hydrogen. And then to turn this into a bond line structure, we're just again going to follow the zigzag, and we've got the OH. So this would be the appropriate bond line structure for this Lewis structure. Again, when we remove the hydrogens, we remove all the carbon hydrogens, but we keep on any hydrogen bound to any other type of atom. And then again, don't draw more than 4 bonds to carbon. That is guaranteed. Sometimes there will be less than, but it will be, you will know that because there will be some sort of formal charge. Okay, so let's go ahead and go through this example, and then I'm going to have you guys try some on your own. You'll come back for the answers. So I mentioned the double bond, right? So I had a carbon with a double bond to oxygen. I was like, oh, you need to try to maintain that trigonal planar geometry. It's the same thing for anything with a triple bond, and this one has a triple bond. It's right here. So let's say that we had carbon triple bound to carbon, and let's say there's stuff going on over here, stuff going on over here. The question here is, what is the hybridization? What is the geometry, the molecular geometry of this carbon, right? It has two other electron groups around it, or its steric number is 2, right? So that tells us that it is sp hybridized and it is linear. So it has 180-degree bond angles, right? We also want to maintain that linearity in our overall structure. So I'm going to demonstrate that on this example. So again, first thing for me, I'm going to go through, count my carbons. I'm going to go ahead and start with the chlorine here, and this hopefully will make sense on why in a second. Because this chlorine is going to be drawn into the bond line structure, and usually I like to have those terminal groups either begin or end as the endpoints, right? So it helps me kind of orient myself for my bond line structure. That doesn't make sense, but hopefully it will in a second. Okay, so we have this guy, one. So we're going to go ahead and count this guy as 1, 2, 3, 4, 5, 6, 7, 8. I'm now going to go ahead and take off all the hydrogens. So I'm going to remove my hydrogens. So now I'm going to go ahead and draw that. So we're left with a chlorine to carbon 2, to carbon 3, to carbon 4, which now has this triple bond here, to carbon 5, which has a single bond to carbon 6, which has a double bond to carbon 7, and then has a single bond, a carbon 7, which has a single bond to carbon 8. Okay, so now we've removed all our hydrogens. We're going to go ahead and start zigzagging. So for whatever reason, I always like to start down. So this guy, if we're going to zigzag, we're going to start the chlorine 1 down. It's going to go up to carbon 2. Going to go down to carbon 3, which is going to go up to carbon 4. Now, this is what I'm talking about maintaining that linearity, right? This carbon and this carbon both have this linear molecular geometry. If I tried to take this guy down with a triple bond, right, that doesn't give me a linear geometry for this carbon 4. It gives me like a bent overall type structure, right? So to maintain our molecular geometry here, this guy is also going to just continue on, right? So it gives this guy an overall linear geometry. So this goes to carbon 5. Carbon 5 is also going to continue on, right? It also has that linear geometry to carbon 6, okay? Now carbon 6 has a trigonal planar geometry because it has 1, 2, and then there's a hydrogen down here, which is 3. So it can zag. We don't have to maintain that linear geometry anymore. So we have a double bond here to carbon 7, and then we'll come back up for carbon 8. We'll keep zigzagging because, again, that guy's also trigonal planar. It can have that zigzag. So for carbon-carbon triple bonds, or triple bonds in general, we have to maintain that linearity, and that has to go into the overall bond line structure, okay? So now, what's going to happen here? We're going to have to depict double and triple bonds in the actual structure, so that's what's going to you're going to be like, oh, well, is this just going to be a straight line? It's not, because there's going to be a triple bond there. We'll see that they're different carbons. But I'm going to go ahead, and we have Cl at the end. So this is carbon 2. Let me go ahead and take this guy. Carbon 2, carbon 3, which goes to carbon 4. Now we're going to depict that triple bond in our bond line structure, which goes up to carbon 5 to carbon 6. This guy goes down to carbon 7, and we come back up to carbon 8. And there is a double bond here in between 6 and 7. Let's make that prettier. So just to make sure, we go ahead and count carbons again. So we've got our chlorine at the end. We've got carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, carbon 7, and carbon 8. And if I wanted to just draw that straight on without any like red in the middle, we again would have our chlorine. Go away. We'd have our chlorine to triple bond to double bond. So this is like ugly, but this is the correct bond line structure given the Lewis structure that we have up here, okay? And so again, this guy in the middle here does end up being like a solid line, but we know that this is a carbon and this is a carbon because we're differentiating that with the triple bond that we've drawn in. So this is 1 carbon, 2 carbon, 3 carbon, 4 carbon in the middle. Okay, so that is that. We'll go ahead and get some practice. So on the next slide, I have a few structures for you guys to go ahead and draw. So go ahead and give this one a try. We have 2 of them here. So let's say we have an A and a B. This one, the left one's really kind of difficult because if you look in here, we've got a bunch of carbons, but note that when we come over here, we end up with a carbon in like a square. That is possible, right? So cyclic structures, or what we would call a cyclic structure, does exist, right? So you can end up with like boxes or pentagons or stuff like that. Not pentagon, but you know what I mean. Hexagons. There's lots of different types of cyclic structures, but just note that that is possible and it does occur. And then over here, we've got some heteroatoms. We've got some triple bonds, some double bonds, but we don't have any type of like cyclic structure in there, or any type of box or whatever. Okay, so go ahead and give this a try. Come back to the answers. Make sure that you're drawing bond line structures correctly. Okay, so I'm going to go ahead and go over these. Again, pause the video if you want to spend more time. I'm going to go ahead and start on the left for A. I'm going to start down here. We're going to call this carbon 1, carbon 2, carbon 3, 4, 5. No, you know what I want to do? I actually want to keep like a backbone as opposed to doing that. So I'm going to start with one of these. We'll call this carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. And then these other carbons, we'll call this one a 10 and this one 11, right? They kind of like are branching off of the overall backbone that is kind of like this structure, okay? They're kind of like what oxygen is here. It just kind of branches off that backbone. So with that, I'm going to go ahead and remove all the hydrogens. So we're going to have carbon 1 to carbon 2, which goes across. There's a double bond here to carbon 3, to carbon 4, to carbon 5, to carbon 6, to carbon 7, which goes up to carbon 8, across to carbon 9. We do have, we'll call this guy, what is this? 11, we'll call this guy 12. We do have a oxygen OH group that branches off of our carbon 6, so we'll go ahead and draw that. We're going to keep that hydrogen on because, again, it's only the carbon-hydrogen bonds we're going to remove. On carbon 4 here, or I don't want to do that, but on carbon 4 here, we have a CH3 group branching off. So we'll put carbon 11 down here, and then on carbon 2, we have a C10 group branching off for another CH3. Okay, so this is removed hydrogens. So now I'm going to go ahead and zigzag. I'm going to start with carbon 1 down. So we have carbon 1. I'm going to maintain just going through the backbone here, and then I'll go ahead and put on those extras at the end. So we have carbon 1 that goes up to carbon 2. There's a double bond here to carbon 3, to carbon 4, to carbon 5, to carbon 6. Right, but then from carbon 6, we go to carbon 7, but then this structure ends up being like a box. So carbon 8 to carbon 9, like a kite, if you will. Again, going back through, we then have an OH group off of carbon 6. We've got another carbon group off of carbon 4. And again, I didn't do that down because I want to keep these bonds as far apart as possible. So that's going to branch up there. And then on carbon 2, I've got another C, carbon 10. Okay, so that's zigzag. So now we're just gonna take away the C's essentially, right? So we've got 1, 2, 3, 4, 5, 6. That's this guy. We'll go up to carbon 6, which ends up being a box structure. There's also an OH here. There's a methyl here. There's a methyl here. And then this carbon 2 to carbon 3 is a double bond. That's really ugly. Let me do that one more time. So again, if we're looking at 1, 2, 3, well, let's do this overarching. What is this? No. I don't see what this is. Come back here. Okay, there we go. Sorry, my bad. So then we've got just kind of broad strokes. And then our thing. Okay, so then we've got to our box. And I think that that's the problem, is the box is really throwing me off. Then we've got this guy, and then this is a double bond. So yeah, it still is ugly, but you know, I'm not the best with drawing with these pens. So again, just to make sure that we've got everything, we've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's a double bond between carbon 2 and carbon 3, and there's an OH group off here. Okay, so that was that one. We'll go over to this guy. Again, I'm going to start numbering this, the oxygen as 1, because it's this continuous line thing that I'm trying to maintain and trying to draw my zigzag structure. So then we've got carbon 2, 3, this is oxygen 4, 5, 6, 7, 8, 9, 10, and then this will be 11. It'll branch off of 9. I'm going to go ahead and remove the hydrogens. I'm going to go, I guess, this way. So we've got an OH, no, I want black. So we've got an OH to carbon 2, carbon 3, oxygen, carbon 5 to carbon 6, which is a triple bond to carbon 7, which is a single bond to carbon 8, which has a double bond to carbon 9, which is single bond to carbon 10, and then again a carbon 11 here. So now we're going to zigzag. I'm going to start with oxygen down as number 1. So we have O, 1 to carbon 2 to carbon 3 to carbon, oh no, there is no carbon 4, it's oxygen 4. So oxygen to carbon 5 to carbon 6. Again, we want to maintain this linearity here between these 4 atoms. So we're going to go up to carbon 7, keep going to carbon 8. Once we hit carbon 8 though, it's going to be triple bound, so now we can go back down to carbon 9 and then up again to carbon 10, and there's this carbon 11 that's also off of carbon 9. Okay, so now we'll go ahead and just replace everything, or replace the carbons. So we end up getting some sort of like 1, 2, 3, 4, 5, up, down, up, double bond. So overall, we're going to have an oxygen. So we've got 1, 2, 3 to an oxygen, carbon, up, triple bond, carbon, down, and then up, and then this guy's a double bond, and there's another carbon here. We keep the hydrogen. We'll go ahead and make sure that we have everything. So we've got, I'm not very sharp, oops, I'm not very sharp with these. These are not the sharpest vertices. So we've got oxygen 1, carbon 2, carbon 3, oxygen 4, carbon 5, carbon 6, carbon 7, carbon 8, carbon 9, carbon 10, carbon 11. And so this should be the correct bond line structure given our initial Lewis structure. In theory, fingers crossed. Okay, so next we're going to talk about functional groups. So one thing that's really nice about bond line structures is that in looking at a bond line structure, you can easily see whether or not something has changed or what has changed, etc. Right? So for example, let's say that we have this reaction down here where we've drawn the condensed formula, right, where we have all of the CH3s together, etc. We do show the double bonds, right? And this is an overall reaction, right? We take our reactant here, we react it with hydrogen in the presence of platinum metal, and this is our overall product, right? If we're looking at this in this condensed formula type depiction, it's really hard to determine what actually happened in this overall reaction, right? All you see is a bunch of C's and H's, and it's not the most obvious about what has actually taken place, or what has occurred, or how this guy has changed, right? Now, if we take that exact same compound, and instead of drawing the condensed formula, we draw the bond line structure, right? We can see that, well, okay, this guy has a double bond in between 1, 2, 3, carbon 3 and carbon 4, right? So there's a double bond here. And going from our reactant to our product over here, same hydrogen, same platinum metal, what's happened to that double bond, right? So this is our carbon 3, this is our carbon 4. That double bond is essentially just changed into a single bond. So we can see for this compound what has happened in this reaction very easy with the bond line structure, where we didn't actually get to see that as well with the condensed formula, okay? So that's really nice with respect to bond line structures, it's allowing us to easily see what types of groups are present in our overall molecule and what happens to those groups in a chemical reaction, okay? Now, specifically, what we're talking about here is something called functional groups. In this specific arrangement of atoms, right, where we have a carbon-carbon double bond, this is a specific functional group. This is called an alkene, okay? And again, it's specific for a carbon-carbon double bond. Now, this reaction overall for all alkenes, all carbon-carbon double bond, is very specific. So anytime you have an alkene and you react it with hydrogen in the presence of platinum metal, you will take this and essentially overall reduce it, which you don't necessarily need to know right now, but turn this into what we call an alkane, right, with an ane at the end. So alkanes are all just carbon-carbon and carbon-hydrogen single bonds, right? So anytime you just have carbon-hydrogen, carbon-carbon single bonds, you have what we call an alkane. Whereas if there is a double bond in there, that's what we call an alkene. So again, ene as opposed to ane. So that's one functional group, what we call functional groups, right? So the overall, what a functional group is when you do have a specific arrangement of atoms in a molecule, they tend to undergo very specific types of chemical reactions, okay? And these rearrangement of atoms are what we actually call functional groups. So alkenes are one of them, right? And we have an example down here of our alkenes. Others that you will need to know and be able to recognize are what we call alkyl halides. So that's one of the first functional groups we ever really deal with their reactivities for. For carbon-carbon triple bonds, right, we call those alkynes. So again, we're going from the ane, which is just single bond, to the ene, where we have a double bond, to the YNE, the alkyne for our carbon-carbon triple bond. You should know all of these guys or be able to recognize them and identify the name of the functional group. This hydroxyl group, this OH group, right? This guy, this is specifically as a functional group called an alcohol group. You should be able to recognize that. If we have a carbon-oxygen double bond, that can be a one of two things. If it's surrounded by other carbons, so again, we have a carbon to a carbon to a carbon, and this guy has the double bond, this is called a ketone. Whereas if one side instead had a hydrogen, again, this is the carbon that's bound to a hydrogen, double bond to an oxygen, but then it's bound to a carbon over here, this is called an aldehyde group. Another particular specific functional group you guys should be aware of is the carboxylic acid. So this is a carbon that has a double bond to an oxygen that is then also bounded to an alcohol group, right? And so if we looked at the bond line structure of that, That's what a carboxylic acid looks like. Again, it's usually bracketed by other carbon chains over here. And then there's an acyl halide, which the hydrogen of the carboxylic acid gets replaced by a halogen. We can ignore that for now. We don't really deal with those that much. And again, just a reminder, the alkyl halides originally, this was just an alkane that had a halogen attached. So halogens are usually chlorine, bromine, or iodine. So you should be able to recognize an alkyl halide, an alkene, an alkyne. You should be able to recognize an alcohol, a ketone, an aldehyde group, as well as a carboxylic acid. And again, you should be able to recognize them in structures and be able to identify their name. So there are a few more. So that's one little page of functional. A couple others that you guys need to be aware of. First off, we have an ether group. So an ether is just an oxygen that's surrounded by just carbons or carbon chains, right? Other stuff that's happening. A good example of that is diethyl ether, right? This oxygen is surrounded by two ethyl groups on either side. You should be aware of that. You should be aware of a thiol. It's whenever you have a SH group or sulfur hydryl group in something. I don't care about sulfides, so you should note and recognize ethers and thiols. You should be able to recognize an aromatic group. So an aromatic group is when you have a cyclic carbon or 6 carbons, right, in this aromatic chain. So it forms a cyclic structure. It's fairly not linear, but it lies flat in the plane. It's trigonal planar. All of these carbons, if you look at their linear geometry, is trigonal planar. It's this, again, 6 carbon cyclic structure with alternating single and double bonds. So that's what we call an aromatic group. I don't care about anhydrides. I do care about esters, so you should be able to recognize an ester. The difference between an ester and an ether is that in an ester, it's got another like carbon-oxygen double bond. So specifically, an ester looks like carbon-oxygen double bond to an oxygen to other stuff, right? It's specific, this part of it. You should be aware of an amide. So an amide is essentially just an ester, but instead of oxygen here, it's a nitrogen. And then you should also be able to recognize an amine. An amine is a nitrogen with just 3 other things bound to it. It can be hydrogen, or it can also be carbon, hydrogen bonds, etc. So ester, thiol, aromatic groups. We don't care about the anhydrides. We do care about esters. We do care about amides, and we do care about amines. So I'm marking these things that I expect you to be able to recognize, just to note that. Okay, so we have one practice little problem here. So I've given you the bond line structures of 2 compounds, right? So we have an A and we have a B, and I'm not going to even try to pronounce them. I'm sure these are some sort of pharmaceutical drugs. What I'm wanting you to do is identify and then also label all of the functional groups. So for example, if I did 1, right, let's say the first one, I would note, oh, this is this like 6 carbon ring structure with these alternating single and double bonds. I know that this is an aromatic group. And so that's what I would say. I would specifically highlight what the functional group is on this structure, and then I would name it off to the side. And if I could name it correctly or spell correctly today. So go ahead and try the rest of this first compound, A, and then try B and see if you can recognize and correctly identify all the functional groups in the compound. So go ahead and pause the video, come back, and then we'll go over the answer. Okay, so I'm going to go through some of these kind of quickly because I'm trying to save time here. I've already identified 1 in the first compound. We have our aromatic group, right? I'm going to identify first this guy up here, right? So specifically, I'm highlighting what the actual functional group is, or the combination, the collection of atoms that make up the functional group. This guy is an ester, right? Because again, we have a carbon, double bound to an oxygen, single bound to another oxygen, and then dot, 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 dot on both sides. That is an ester. I'm going to move to the left here. We've got a nitrogen. that has what we call a carbon, and a hydrogen off to the side. So specifically this guy, let me highlight, this guy is what we would call an amine group. This one to the next here is kind of tricky. So we have a carbon that's double bound to an oxygen, right? But then it also has a bond to nitrogen. The nitrogen goes off and does other stuff. Forms, again, another cyclic structure here. But this carbon double bound to an oxygen to a nitrogen, this is an amide group. And then as we come off to the end here, we've got a carbon that's double bound to an oxygen that is also bound to a OH, an alcohol group. So this is not an alcohol by itself. It's not a ketone. This is specifically a carboxylic acid. Carboxylic. I think I'm just spelling wrong today. Acid. Probably. Okay, so then that's A. So how many do we have? We had aromatic, ester, amide, amine, carboxylic acid, and that was it. Okay, moving on to B, similar type things. We've got nitrogen bound to carbon, and hydrogen. So again, this guy is an amine group. So we've got amine. We'll continue to the right. Now we've just got a carbon to an oxygen or a carbon to a hydroxyl OH group, right? There's no like double bonds or anything like that around. So this is just specifically an alcohol. We do have an oxygen that leads into this aromatic group, but these are actually just two separate things, right? This oxygen that has a bond to carbon on both sides, this is an ether. And then this is an aromatic. There was no like combination of an aromatic ring with an oxygen. So those are just two separate functional groups. And then finally at the end, this is also kind of confusing. We have a carbon double bound to an oxygen that's bound to a nitrogen. This nitrogen also has two hydrogen. That's like what the H2 is. It's got two bonds to hydrogen. But again, that carbon double bound to oxygen bound to nitrogen is an amide group. Okay, so hopefully that's clear. Let me know if it's not. And then I would just focus on, again, unfortunately, memorizing those functional groups and what they look like and what their names are.